Dear lovely viewers, welcome to another fascinating math problem. Welcome back to my channel. Today we have another exciting problem, a system of simultaneous equations. So let's go see the problem and go through the solution together. So we have here these Diophantine equations from number theory, x plus y equal to 2, x to the fifth plus y to the fifth equal to 82. So this system of equations is quite funky and esoteric, but our mandate is to use a simpler approach that can make it comprehensible. Now, if you take a look at this problem, if you've taken Algebra 1 in high school, you can use the substitution method. Though that's not the method I would use to solve it, but I want to make a point from it. So from the first equation, we can say that x is equal to 2 minus y. Then I will then, in place of x here, I will write 2 minus y. I'll then be having 2 minus y all to the fifth plus y to the fifth equal to 82. So I will then expand this. That's going to give me 32 minus, 80y plus 80y squared minus 40y cubed plus 10y to the fourth minus y to the fifth plus y to the fifth equal to 82. I actually memorized this. So you can actually expand this using Pascal triangle. But the reason why I'm even writing these equations out is to make a point, or rather a statement. So the highest power here, y to the fifth will cancel out. They will leave the system. We're going to be left with 10y to the fourth minus 40y cubed plus 80y squared minus 80y, plus 32 minus 82 equal to 0. So if I clean this up, I'm going to be having 10y to the fourth minus 40y cubed plus 80y squared minus 80y minus 50 equal to 0. It's actually a quartic polynomial. I had to do this so that I would be able to know that this Diophantine equations actually is a quartic polynomial which has 4 solutions for x, or rather 4 values for x and 4 values for y. Then again, I want to see if this is going to give me a rational, if I'm going to have rational roots. So first and foremost, I will divide through by 10. That would then be y to the fourth minus 4y cubed plus 8y squared minus 8y minus 5 equal to 0. Here, 5 is a prime number. It only has 2 factors, 1 and 5. So from the rational root theorem, if I divide 5 by 1, that will be 5, because the leading coefficient here to the highest power is 1. So if I stick in 1 here, that's not going to give me 0 from the remainder, from the factor theorem. Then if I stick in 5 here, I'm also going to get 0. So it therefore means that this quartic polynomial does not have rational roots. So I had to think outside the box, because this is actually an Olympiad problem. Then the only option is to use algebraic identities, which are very vital tools in algebra. Then first, we shall start from the square of sum. We know that, we recall that s squared, let me just write s plus y all squared is actually s squared plus 2sy plus y squared. Okay? Now, from the very first equation, x plus y is equal to 2. I can write 2 squared equal to, I'll try to bring x squared and y squared together because I need them. X squared plus y squared plus 2sy. Okay, this makes sense. Then, for me to make things simpler, I have to make a substitution here. I need to say let k equal to sy. This is going to help me to refine the context of this problem. Then I'll then be having 4 equal to x squared plus y squared plus 2k. That's what I'm going to have. So if I then isolate x squared and y squared, let me write this way, 2k. So from here, I'm going to be having x squared plus y squared equal to, okay, 4 minus 2k. I'll call this equation number 1. Then, after square of sum, I will also use cube of sum. I also know that x plus y all cube is going to give me x cube plus y cube plus 3x squared y plus 3xy squared. I have solved problem involving this. It's very easy to master. Then x plus y is equal to 2. We are going to be having 2 cube here. Then we are going to be having x cube plus y cube. Then Then here I will factor out 3xy. I'll be having 3xy into x plus y. Okay? All right. Then this is going to give me 8. I'll have x cubed plus y cubed. Sy is equal to k. X plus y is equal to 2. I'll be having 3k times 2, which is 6k. I'll write 6k. Then I can then say that x cubed plus y cubed equal to 8 minus 6k. I'll call this equation number 2. So if I multiply equation 1 and 2, my homecoming is guaranteed. So equation 1, I have x squared plus y squared to the left. Then I have x cubed plus y cubed in equation 2. Then I'll multiply 4 minus 2k, 8 minus 6k. So if you multiply equation 1 and 2, you multiply the left sides together and the right sides together. So if I distribute here, you can see the creativity and the simplicity of this approach. If I say x squared multiply x to the, x cubed, that would be x to the 5th. Okay, x to the power of 5. Then here, x squared multiply y cubed, that would be x squared y cubed. Okay. Here I will have y squared multiply x cubed, that would be x cubed y squared. Then y squared multiply y cubed, that would be y to the 5th. So we'll have y to the 5th. Then on the right hand side, we have 4 multiply 8, which is 32. 4 multiply negative 6k, that will be negative, 24k. I'm done with using 4 to distribute. I will then use negative 2 to distribute this second parenthesis. I'll be having negative 16k. Then the last one will be negative 2k multiply negative 6k, which is 12k squared. This is interesting, right? Okay. Now, the left-hand side, I have to clean it up. I'll write x to the 5th plus y to the 5th. All right. Then I'll write x squared y cubed. Then I'll write x cubed y squared. Okay, then to the right, I'm going to be having 12k squared minus, okay, negative 24k and negative 16k. That will give negative 40k plus 32. So on the left, I can still make something out by factorizing. I think I have to take out the left side of the board. It's a very interesting problem. A little bit funky, but we are going to simplify it regardless. Okay, we have s to the fifth plus y to the fifth. Then, like I said, I want to factor out something here. I think s squared, y squared is common. The HCF of these two guys, s squared, y squared. I'll write s squared, y squared, open a parenthesis. If I divide, I will have s plus y left. Okay? Then on the right side, I have 12k squared minus 40k plus 32. Then s to the fifth plus y to the fifth is 82. Then s squared, y squared, I can write this to be 82 plus sy all squared, s plus y. Okay, so this is okay. So it becomes 12k squared minus 40k plus 32. And xy is equal to k. I'll then be having 82 plus k squared. S plus y is equal to 2, the first equation. I will write 2k squared there. Then on the right side, I have 12k squared minus 40k plus 32. So we have a quadratic equation in our hand. So I will say, okay, 12k squared minus 40k plus 32 minus 2k squared minus 82, everything equal to 0. So 12k squared minus 2k squared, that will be 10k squared. Then minus 40k stays. 32 minus 82, that will be minus 50. Everything equal to 0. If I divide through by 10, I'll be having k squared minus 4k minus 5 equal to 0. So, guys, I can factorize this directly because of the nature of the problem. This is actually k minus 1, okay? Minus 1 or plus 1. K plus 1, k minus 5 equal to 0, okay? Okay? So here we are going to be having k plus 1 equal to 0, k minus 5 equal to 0. So k is equal to negative 1, then, or k is equal to 5. So from the, okay, substitution we made along the line, we said k is equal to xy. So we can then say that sy equal to negative 1, then sy equal to 5. So this is the punchline in this solution. Now, I don't want to be solving simultaneous, no, I don't want to be solving linear simultaneous equation and quadratics to take longer time. So I will then use another famous algebraic identity to finish this problem. Now, because of the fact that we have xy equal to negative 1, and again we have xy equal to 5, I am going to make do with this formula s minus y equal to s plus y all squared minus 4sy. So in quadratic equations, for symmetric properties of roots, we know that alpha minus beta is the square root of alpha plus beta all squared minus 4 alpha beta. You've come across this before. So if I can be able to get s minus y, I already have s plus y. I think that would be a simpler, way or approach rather than solving quadratics and simultaneous equations together. So I would then say for case one, we are having sy equal to -1. So I can then say s minus y, that will be the square root. Then we know that s plus y is equal to 2. That will be 2 squared minus, okay, sy is -1. -4 multiply -1, that will be +4. And because we are taking square root, I will attach plus and minus. So I'll then be having s minus y equal to plus and minus the square root of 4 plus 4, which is the square root of 8. Now, the square root of 8 is the square root of 2 multiplied the square root of 4. So I will have s minus y equal to plus minus 2 rad 2. So for subcase 1, we are going to be having s plus y equal to 2, s minus y. I will take the positive, which is 2 rad 2. So if I add these two equations, I will find the value of x, which is the first solution. Like I said at the beginning, it's a bit complicated, actually, but it's actually also easy if you put your mind into it. So if I add these two equations, I'll be having 2x. While we eliminate, I'll then be having 2 plus 2 rad 2. Then, so 2s, I'll factor out 2. So it needs to be easier like that. So s will be 2 into 1 plus rad 2 divided by 2. So this is going to be 1 plus rad 2. So this is our first solution. Then we move forward. I think I have to get my other marker. It's a nice problem with a very beautiful solution. Then if I substitute into this equation here, I'm going to be having, okay, y, let me write, since s plus y equal to 2, it implies that y equal to 2 minus x. So I'm going to be having the first value of y to be y equal to 2 minus 1 plus rad 2. So if I open this parenthesis, I'll then be having 2 minus 1 minus rad 2. And that's going to be 1 plus rad 2. So this is the first value for y. So I can then say s1 y1 equal to 1 plus rad 2. I'll put comma. Okay, it's actually a minus sign, very sorry. Then 1 minus rad 2. We are done. Then subcase 2. Subcase 2. We are then having xy equal to 5. No. We have used the positive value for s minus y we need to use the negative value. Very sorry for this. I'm overexcited. Okay. Very interesting problem. Okay. Similarly, s plus y equal to 2. Then we have s minus y equal to 2 rad 2. Supposed to have called this one subcase 2, regardless. Then I'm going to have a negative value here because we said that the square root of 8 is plus or minus 2 rad 2. Then I am going to subtract these two equations. Because of the negative sign here, I will say subtract equation 2 from equation 1. Then that's going to give us 2y equal to, okay, 2 plus 2 rad 2. That's what we are going to have there. That's what we are going to have. So I can also factorize this. 2y equal to 2 into 1 plus rad 2. Okay, I'll go to this other side. This will actually give us the second solution set for x and y. So y is going to be 2 into 1 plus rad 2 divided by 2. And this will give us 1 plus rad 2. Okay, then I also know that s plus y equal to 2. So if I have y, I can easily get x by saying 2 minus y, which is 2 minus 1 plus rad 2 is going to give us 1 minus rad 2. Okay, the second solutions, let me call this s2y2. That is actually going to be 1 minus rad 2, comma, then 1 plus rad 2. So the next thing to do is going to be, okay, let's consider case 2. Case 2, sy is equal to 5. Sy is equal to 5. Then s minus y will then be square root. I'll write plus or minus. Then I'll write 2 squared, okay, minus, okay, the formula we are using here is s minus y equal to square root s plus y all squared minus 4sy. So that will now be 4 multiplied 5, which is 20. So s minus y will now be plus or minus the square root of negative 16. So these are actually complex solutions. So the square root of negative 16, that's going to give us s minus y equal to plus or minus 4 iota, 4i, where I is an imaginary number. In the Greek letter, this is actually called iota. So I can then find the values of x and y. So I will take out this side of the board. We are at the very last lap to conclude this monstrous problem. So now that we know that s plus y equal to 2, then we'll take the positive value first. So x minus y, that would then be 4 iota, which is the positive value there. So I will add. So this is going to give me 2s equal to 2 plus 4 iota. If I divide both sides by 2, I'll be having s equal to 2 plus 4 iota divided by 2, which will give me 1 plus 2 iota. Then I also know that x plus y is equal to 2. Then to get y, that will be 2 minus x. And what's the value of x? That is 1 plus 2 iota. So y will then be 2 minus 1 plus 2 iota. So if I put this in parentheses, it's actually 1. So I'm going to be having 2 minus 1, which is 1 because of time, minus 2 iota. So I will then say s3, y3. Okay, let me put it in parentheses. This will then be 1 plus 2 iota, 1 plus 2 iota, comma, 1 minus 2 iota, comma. This is the third solution. Then I will also consider when s minus y is negative. Okay, I'll then be having similarly, okay, when s minus y is equal to negative 4i, I'm going to be having s plus y equal to 2, then s minus y equal to negative 4 iota. I'm also going to solve this simultaneous equation. Okay, s minus y equal to negative 4 iota. So in this case, I am going to subtract. So I will subtract. We're now going to be having, okay, something very interesting. I'll subtract 2 from 1. It means that 2y equal to 2 plus 4i. Okay, that will be 2 minus 4i. Then y will be 2 plus 4i divided by 2, which is equal to 1 plus 2 iota. So s is going to be 2 minus 1 plus 2 iota. That will be 2 minus 1 minus 2 iota, which is 1 minus 2 iota. So I can then write the last set of solutions, S4, Y4. That would then be 1 minus 2 iota, comma, then, okay, 1 plus 2 iota for the value of y. So this is the last set of solutions. If I were to recall the whole set of solutions, we know that S1, Y1, that will be 1 plus rad2, comma, 1 minus rad2. Then S2, Y2, comma, is actually equal to S1, comma, Y1. That would then be 1 minus rad2. Okay. 1 minus rad2 is an alternation. Then y will be 1 plus rad2. Then S3Y3. Let me put command there. Since they are here. The first solution for S is 1 plus 2 iota, comma, then 1 minus 2 iota. So S to the fourth and Y to the fourth. That's going to give us what we have here, 1 minus 2 iota, comma, 1 plus 2 iota. So you can see the alternation in the solutions. So guys, we've come to the end of an exciting problem. Please give this video a like. Don't forget to share with your learning friends and colleagues, and make sure you subscribe and turn on the post notification so that you don't miss out in our next video. See you next time. Bye.